in this topic, we'll have the introduction to Open RAN. Now we move on to the topics. So what is RAN? The RAN components, the RAN and OSI layer, what is 5G, RAN architecture, what is Open RAN, the GPP or the general purpose processors, hardware and open systems, the Open RAN ecosystem, deployment and trials, and we'll end with the key learning points. As you can see, it will start, the discussion will start from the macro view of what is RAN, the radio access network, from the typical deployment that we have in the industry. And then we'll zoom in to a particular technology, which is 5G. Okay, so 5G is employing the radio access network technology. And then after that, how do we implement 5G? So there are different types of implementation of 5G. So it could be implemented using a typical RAN solution or a traditional RAN solution. And of course, we can also deploy 5G using Open RAN. Okay, so because there's a lot of confusion on that kind of demarcation, that is 5G an Open RAN or Open RAN is 5G. Okay, so the correct answer is you can deploy 5G using Open RAN. Okay, so because 5G is a technology, while Open RAN is a new movement or implementation approach of deploying a technology like 5G. Okay, now let's move on to RAN. So what is radio access network? As you can see, this is the typical mobile network coverage that we gathered using the application called the embark. You can also download this app. This is a free app, but this is not a pure representation of the mobile operators coverage. It greatly depends on the participation of subscribers. If they want to participate or give their data through the app, so we can get what type of technology are currently serving their system. So it could be 2G, 3G, 4G, or even 5G. And surprisingly, in Metro Manila, you can see here that there's a lot of 5G signals already. Okay, so meaning operators like Smart, Globe, or Dito are focusing on these areas. And the main reason is because the business case is healthy in this area if we deploy 5G, because most of the people are owning a 5G capable device already, compared to other areas where people are not so much of upgrading their devices. Although some people are upgrading their mobile terminals to 5G, but the numbers are not comparable compared with NCR or National Capital Region. Okay, so this is the type of signal level that we can gather from NPerf. Okay, so now let's move to the fundamentals of wireless telecommunications system components. So it's as easy as 1, 2, 3, as we have discussed in the radio access network. So it's just connecting the dots from point 1 to point 2 to point 3. So it's an easy as 1, 2, and 3. Number 1, you have the user terminals. Okay, so the user terminals, these are the user equipment or your mobile station, basically your phone. And then this is connected wirelessly or connected by an invisible road through the radio access network, or typically known as cell sites. So these are the RAN or the radio access network. And the radio access network is then connected to the core network. So where exchange of calls are happening, and most of our subscriptions are stored as well. And the connection between the radio access network and the core network is called the backhaul. And we can implement this using the microwave, the fiber optic, or even satellite. It depends on the application and the severity of the area. For example, if we can connect it via microwave wirelessly, we can do it. But if we are requiring more data transmission and needs fiber. Fiber is a higher capacity transmission, and you can lay out or lay down fibers, and no one is restricting you to lay down fibers or dig in on the side of the road. You can implement fiber optic. But if there are challenges in implementing microwave or fiber optic, like in the remote islands or mountainous areas of the Philippines, you can use satellite. So in the recent application of deployment of different cell sites, like for example, if you want to deploy a cell site in Kalayaan Islands, fiber optic is not practical to do that, and microwave is not also possible because that is very far. So the limitation is already caused by the curvature of the Earth. Okay, so microwave is not anymore giving you a sufficient line of sight. That's why the connection from the radio access network from the cell site that you can build in Pag-asa in the Kalayaan Islands can be connected to the core network here in Metro Manila through satellite. So the satellite could be a very small aperture terminal or via Starlink, okay, via low Earth orbit satellites. So these three components are very important. So in any kind of wireless telecommunications, either 2G, 3G, 4G, or even 5G, these three components are should be or must be present. Okay, so you need to have a user terminal, you need to have a radio access network, and it must be connected to a core network. For example, you have a 5G phone capable. If the radio access network is not 5G capable, you cannot enjoy a 5G service. Okay, so it must be an end-to-end capability of the network. So from a 5G terminal, it must be served by a 5G radio access network and a 5G capable core network. Okay. Okay, so let's move on to the radio access network. So the radio access network is the one that gives the mobile coverage. So this is the one that gives a signal. So this is the part of the cellular network that is nearest to the subscribers. So that's why you can see it all around you. And the location of the radio access network is widely distributed. So you can see it almost everywhere. And thousands of RAN elements create seamless coverage and mobility. So to give you a ballpark figure of how many cell sites do we have in terms of tower numbers, for example, in Smart or in Globe or in Dito, if you combine them, it's less than 50,000. Okay, so that's the typical number of our cell sites here. Now, we put different cell sites in different parts of the Philippines to give us this kind of signal level. So it's a correct thinking that if there are no cell sites nearby within 5 kilometers, you will not expect a mobile coverage or signal. So we need to have a presence of cell site in a certain area to have a mobile signal or signal sa inyong mga phones. That's why in one of the use cases that we try to create here in Asia Open Academy is to connect those GDAS areas, meaning those geographically isolated and disadvantaged areas. So these are the areas in the Philippines where it's very hard to reach. No, you can go there by a foot or riding a bangka or a habal-habal, the motorcycle. So building a cell site near that village is also challenging. So if that is a challenge already to operator, so we cannot expect any signal coverage in that area, and that creates that what we so call the digital divide. So meaning those people are not only isolated physically, they are also isolated digitally. Okay, so they are not also connected to the internet. So there are a lot of challenges, right? If there are no digital connections. So they cannot have access to, for example, medical services, to doctors. So it would take them around 4 hours to from their village going to the nearest municipal health center. So that's why we are proposing to build a new type of radio access network that could serve them, which is a cost-effective solution and could also give a same quality of service like the typical radio access network, and that's where Open RAN will come. Okay, so that's why we are putting different types of radio access network all around the country. And you can see it's only selected areas where 5G is being deployed. Okay, because this is mostly driven by the demand and also the business case. Okay, so you can see there's very few in Visayas area or in other part of Bicol region, the deployment of 5G. But you can see that the deployment of 4G and 4G and 4G plus is already matured. So you can expect a lot of areas here in the Philippines with LTE connections. Okay. Okay, so you just showing that we are building a lot of cell sites here. Okay, so RAN is all around you. So you can see it everywhere. So these are the different types of RAN or different structures of RAN. These are, you can find a cell site near the roadside, in the province, on the top of the mountain, even on beach, rooftop, or even inside the malls. Now, RAN also evolves through time. So it started from 1G. We call it the foundation of the mobile technology. So this is the first time where people started to become mobile when using their phone. We started with the POTS, plain old telephone system where it is installed inside your house. And if you want to make a call, you need to go inside your house and then make the call. Or if someone is calling you, you need to go inside your house and then answer the call. But when during the arrival of 1G, this is the first time that we became mobile. You can answer a call anywhere and anytime. Okay, so that's why we call it. It is called the foundation of the mobile technology. So the most famous type of 1G technology were the AMPs, the Advanced Mobile Phone System, the TACS, the Total Access Communication System, and the NMT, the Nordic Mobile Telephony. Okay, so these are analog technology. And then 2G came in 1990. So this is the digital digital type of cellular technology where mobile telephony was what we can say it's democratized. Everybody can have their mobile phone because it's much or it's cheaper compared to a traditional or the or the um typical 1G phone where only the rich can buy. So this has become a democratized technology. And when it came to the Philippines, the killer application was the text message or SMS, the short message service. So the famous technology under the 2G is the GSM, the Global System for Mobile Communications. And then there was a rapid demand for use of faster data speeds, and that's why the foundation of the mobile broadband has emerged in the likes of 3G or the universal mobile telephony or telephone services, okay, or system. So this was released in 2000 where people have given the opportunity to have a mobile broadband. So mobile broadband means you can connect to the internet from 1 Mbps and above. Okay, using the 2G, it's still in the kbps from 64 kbps to up to 384 kbps only. But for 3G, we have reached one from 1 Mbps up to 42 Mbps. Next was the 4G, the fourth generation mobile communications. And the famous technology here is the LTE, or the long-term evolution. So this was released in 2010. So we call it the further enhanced mobile broadband. Okay, so 4G has enabled services like streaming videos, online gaming, and mobile payments. So it also paved the way for the IoT, or the Internet of Things, and other emerging technologies. These were also the time where we enjoyed 100 Mbps using our mobile phones. So you can see the big leap of data transmission from 1 Mbps to 100 Mbps. And now we are in the era of 5G, okay, or the fifth generation mobile communications. So 5G promises to be even faster and more capable than 4G. So the data speeds are about 100 times. So it could be around 1,000 Mbps. So in the recent trials and testing conducted by our current operators, they have achieved around 1,000 Mbps. That is 1 gigabit per second. Okay, so imagine what can be done now using that kind of speed. That's why in 5G, it's not just only for mobile broadband. It has a diverse opportunities because it could give us three use cases, no? The EMBB, the enhanced mobile broadband, the MMTC, or the massive machine type communications, and the URLLC, or the ultra reliable and low latency communications. Okay. Now, so we have identified what is RAN and what are the evolutions that happen in the RAN. Now let's check what are the different parts of a radio access network. So let's go to the RAN anatomy 101. Okay, so this is the typical architecture. So you have the core network, you have the radio access network, and then you have here the terminal, no? The user terminals. So I'll just add a user terminal here. Okay. Okay, and then connected wirelessly. Okay. So first we have the tower structure. Okay, so this is the physical structure that supports the radio access network components, such as the antennas, okay, and the other components such as the radios and the cables. No, so the radios are connected to the antennas using a jumper cable. Okay, so these are copper cables connection. And then the radio access network is connected to the baseband unit. So the baseband unit acts like a processor. Typical, just like your similar, just like a typical computer. So you have your processor. So CPU, central processing unit, to activate all the functionalities needed by your cell site. And the radio access net and the remote radio unit is the one that is producing the electromagnetic energy. And the antennas are the one propagating it into certain directions and controlling your patterns. Okay. So the baseband unit is connected to the RAN through the fiber optic cable called the common public radio interface. Okay. It is a fiber optic cable. And the baseband unit is usually enclosed in an outdoor cabinet or even in the cabin where the uh hold on where the where the power source or the backup battery and the ventilation or air conditioning is also located. Okay. Yeah, so those are the typical parts of the radio access network. So this is the transmission part, or the backhaul connection. In this example, we used a microwave antenna. Okay. So these are the components of the radio access network. Okay, so the RRU, or the remote radio unit, is a radio transceiver that communicates with the mobile devices. So this is how the RRU or the remote radio unit looks like. So these are typically located near the antenna to reduce the transmission loss, no, between the radio unit and the antenna to maximize the power transmission. And the CPRI is the one that is connecting the RRU and the BBU. So we call it the common public radio interface. So this is a high-speed transmission of data over a fiber optic cable. And usually the common public radio interface are proprietary, meaning the existing vendors like Huawei, Ericsson, and Nokia are the one who design the standards, how the CPRI will be connecting these two radios. That's why if you buy one equipment from typical, for example, H vendor, the CPRI must be bought also from them. And then you will connect it to a baseband unit that you need to buy also from them. And the software as well are coming from them. But typically, it's a closed system. You need to buy everything from them. And now, in what's happening in the industry, even the services and the integration, you buy it from them. Okay, so the licenses, the features, everything is coming from them. Just like if you own a car, so you bought you for example you bought a Fortuner, you buy the spare tire to Toyota as well, and then you buy the cleaning um tools from Toyota, and you also use fuel from Toyota. Everything will be bought from Toyota. So that's what we call the proprietary. So you cannot buy from somebody else. That's why whenever Toyota said, okay, we'll have a price hike on the amount of new tires. So from 6,000 pesos, we will be upgrading it to 10,000 pesos per tire. So you are locked to that kind of business model. So operators don't have any more choice. Okay. So the tendency is that if the price of the hardware, the software, and the services or building a cell site goes up, the end result would be on the subscriber side. The price of the internet and the price of the connection will be also high, right? Because the production of the materials is taking a lot of money. So when they sell it so that it could be profitable, there's a possibility that the price of the data could be high. Now, if we can lower either the cost of the hardware or cost of the software or even the cost of the implementation, there's a possibility that the price could go lower in terms of for the subscribers perspective. That is one of the promise of Open RAN because we are opening the system, meaning you can buy one radio unit from one vendor like Parallel Wireless or Mavenir. We can buy the CPRI also from those vendors. We can also buy a baseband unit or a typical server from Dell, okay? And then install the software from one vendor as well, probably from Capgemini. So you have a lot of options to choose from. It depends on your specifications or requirements. Now, if I want to have a 9-inch rim for my Toyota Fortuner, or I want to have a more high octane fuel for my Fortuner, so I have the choice, no? So it's either you want to have a high performance vehicle or a more efficient vehicle, so that you can, for example, if you're using your Fortuner to transfer passengers only, right? And then you want to have a profit in terms of the ride sharing. So you can select fuel that you feel that is more efficient, so that you can maximize, the the um, the utilization of your vehicle, and then you can get profit from your subscriber, from your passengers. So that's just a typical example. Okay, so that's the promise of Open Run. That's why one of the motivation is to lower down the cost of building a cell site. And aside from that, of course, there would be some functionalities like you will see on the next slide that our application of the artificial intelligence is necessary, because as we build cell sites, more cell sites, and as the technology increases and the number of technologies are getting vast, you will see that the management of the network becomes more complicated. And it's very difficult, especially if that will be handled by a typical engineer, even a magna cum laude engineer or a top one electronics engineer cannot handle it, the complexity of the network. There must be an automation or a program or an intelligence that could handle it more efficiently. And that's where the artificial intelligence comes in. Okay. So later on we'll discuss more about it. Okay, so this is typical connection. So the baseband unit, as I mentioned, so this is the one responsible for processing the baseband signals. And most of the time, this is placed in the equipment room and connected with the RRU with the fiber optic cable. Okay, so if you look at one cell site today, you cannot see the baseband unit, because most of the time, the baseband unit is located at the bottom of the tower, and most of the time there is a fence, no? So you cannot see this. What you can see most of the time is the antennas, and if you're lucky enough, you will see some part of the RRU. But the baseband unit you cannot see because of the height of the fence. Okay? Great. Now let's move on to, we're finished with the hardware component now of the RAN. Now let's go to the software part, or the layers that we are using in the RAN. Okay? So, when we talk about RAN, so these are divided into different layers. So each of which is responsible for a different aspect of the system. So one common way of conceptualizing these layers is through the what we so called the open systems interconnection, or the OSI model. So this is a conceptual framework that describes the communication functions of a telecommunications or computing system. So how each layer or component is talking to each other. So that is why that is what we so called the OSI model. So in the OSI model, we have um, 7 layers, and as I mentioned, this OSI model is described as the how uh, standardized, no, a computer or telecommunication systems talk to each other, regardless of how it is built or what technology it uses. Okay, so we have 7 layers. So from physical layer, from down data link layer, network layer, transport layer, session, presentation, and application. Okay. So the physical layer is the one responsible for the transmission and the reception of raw data over a physical medium. So it includes copper or fiber optics. Now, the data link layer is the one responsible for the reliable transmission of data over a shared physical medium. So you can see the protocols such as the Ethernet or the Wi-Fi. Next is the network layer. So where the routing of data between different devices on a network using a protocol, such as like IP or MPLS. And then we have the transport layer. So this is responsible for ensuring a reliable and efficient data transfer between devices on the network using a protocol like TCP or UDP. And the session layer, okay, responsible for establishing and managing communication sessions between devices on a network, like they're using a protocol like RPC and NetBIOS. And of course, the presentation layer, okay, so for formatting and presenting data to be transmitted over a network, such as protocols and ASCII or JPEG. And of course, the application layer. Okay, so if we will use this 7 layer and we will map the layers of the radio access network, you can see that the functionality of the RRU or the radio link or the radio unit and the baseband unit falls within these 3 layers. Okay, and the other layers are located in other parts of the network, like such as core, from the UE or the transmission. Okay, so in the radio access network, you can see these 3 layers: the physical, the data link, and the network layer. Okay. Now, if you want to memorize these application, these OSI layers from physical, data, network, transport, session, presentation, and application, you can use this mnemonics. This is all people seem to need data processing. Yeah. So this is the mnemonics now to memorize the sequence, the correct sequence of those application layout, those OSI layers. Now, if you want to use it in Tagalog or in Filipino and you are in abroad, so most of the time I use this mnemonics in abroad. Uh, we call it ang pulis sa tulay na dapa, with that kind of kind of intonation. No? Okay. Ang pulis tulay na dapa. Pero sa Pilipinas, ang pulis sa tulay na dapa. But if you're in the outside the Philippines, yeah, you make it slang. Okay. So this is the mapping of those layers compared to the OSI layer. So these are the different layers from layer 1 to 3. And then if you will see, the radio access network have different protocols as well. So different components have a different protocols. So in telecommunication, you can see usually the RRC, okay, the radio resource um, connection, okay, the PDCP, the Packet Data Convergence Protocol, the Radio Link Control, the Medium Access Control, the Air Interface. No? So this is the journey of the data. So from the production of, for example, you would like to call somebody. So from analog, it will be converted by your phone into digital, and then for that digital transmission, for digital data to be transmitted, it needs to be converted, okay, converted and processed into usable form so that the system can transmit it on the other side of the network. And that kind of transformation of data involves this kind of protocols. Okay, so this what is happening no in the RAN and OSI layers. Mhm. Okay, so yan. So palagay lang natin lang ng iba yan. So if we will review the architecture of the wireless telecommunications, you still have the UE. Okay, so this is the user terminal. Okay, you have the radio access network. So this is the 1, this is the 2, and this is the 3. Okay, so remember this, no? So connecting the dots, connecting 1, 2, and 3. Now in this slide, you will see the separation no, of or the components of each point. So for the UE, so you have this mobile phone. For the radio access network, you will see the antenna, the RRU, and the baseband unit. So in the RRU, so this is where the physical layer comes in. So this is the RF conversion. That is from analog to digital or digital to analog. So from analog to digital, no? So there's a conversion of data already. Now, if that data will be transmitted from the RRU going to the BBU, so these are the different protocols that's happening. Okay. So there is what we so called the physical layer. So you have the error correction. So if there's a error in the transmission of the number of bits or data, coding, so you are adding more bits to add more redundancy, okay, to increase the integrity of your transmission. You also have the modulation, okay, so you're converting that analog signal, no, to a digital a component, and then you can demodulate also. So these were the reverse of the modulation, and the resource element mapper. So where are those number of bits located in the spectrum or the spectrum resource, no? And then you have the multiplexing, the medium access layer, where you are combining different signals coming inside the cell site. The RLC, the radio link control, the segmentation, concatenation, and if you have some that you can also detect if there's a duplicate transmission happen. Okay, so segmentation happens that if there's it's a long trail of bits that is sent through the network, the system will cut a chunk of that transmission. So we call it the segmentation. Okay. So the reverse of that is the concatenation. So it will get the first chunk and then get the second chunk and then combine it. So that is the concatenation. And next is the PDCP, the IP header compression. So this is where you put you are compressing the signal so that it's easier for you to transmit. So imagine it's just like a packaging. If you want to transmit or want to send something from Lazada. Okay, so you want to, for example, you want to um deliver or send a laptop to your kid in the Philippines, no? So you will buy a laptop here and then you will send it via courier. So your laptop will go into this process. Okay? So they will check the laptop if there are some damages, okay? If there's some damages, they will return it to you. Okay, please check again your laptop if there's a physical damage. Okay, so if there's nothing, okay, we can check it. And then the concatenation, you're not the only one. You're not the only one sending laptops, right? So there's a lot of people sending laptops as well. So they are combining those laptops. Okay, so these are the laptops going to the Philippines. So they are arranging it. So the PDCP, they are putting header already in your packages. So these are for the Philippines, but in the Philippines, this is going to North Luzon, NCR, South Luzon, Visayas, or Mindanao. Okay. Now the RRC is the broadcast. Okay. So once it is deployed already, okay. So if you want to page somebody, you want to call somebody, so this is where the signaling coming in. So you are paging the caller or are the recipient of the call. So same thing with the delivery or the courier or the Lazada, no? So once they identify the address, so somebody will be knocking at your door that there is a delivery for you. And then you need confirmation if that is you, okay? And if you are really expecting this delivery or not. So it's the same thing like that, no? So it's a typical transmission system. The only difference is that what we are delivering is data, the number of bits, zeros and ones, compared to the courier services like Lazada. Okay, so this is the RAN and OSI layer. And you will see here, the most important here is that in terms of Open RAN, you will see Open RAN is almost the same as a typical radio access network. If you look at the equipment of Open RAN, hardware is almost the same. There will be no demarcation. This is Open RAN. No? Probably in the branding, like Parallel Wireless or Mavenir. So they are known to be Open RAN. But if you look at, for example, an Ericsson or a Nokia, if you compare this RRU and BBU, it looks almost the same. Okay, so there's no complete demarcation which one is Open RAN or not. But you can see that these functionalities will also be the same in Open RAN. Okay, which it will be the same because this is provided by a specific standard called the 3GPP. And the Open RAN will also use the 3GPP standard. Okay, so the only difference is the implementation. Now, for the closed system, typical vendors give a specific lock, no, for this equipment to talk to each other. Now, Open RAN will become open. When you say open, no, it's not open for threats or something. Meaning, everybody knows what's happening inside. Okay, so and the way the equipment talks to each other is that it is defined by a specific standard called the 3GPP and the ORAN Alliance. So everybody knows what's happening inside based on an agreed standard. Okay, so previously, if you buy something from Huawei, so they are the one, although that is referring also to 3GPP standard, but what is happening is that they put another proprietary um, segment in that kind of in their software that nobody knows except them. Okay, so we call it sometimes the black box, no? Ang mahiwagang black box. Okay, so we don't because we don't know what's happening. Okay, so that's the difference, no? So you can see that the openness is introduced in Open RAN. Okay. Okay, so you will see here that these protocols will be separated in each segment. No, some of the functionalities or protocols can be defined. You will see here, no, what will happen in Open RAN is that the BBU will be separated into two: the CU and the DU. And some of the functionalities like PDCP, RLC can be defined in the CU, and the MAC and the physical can be defined in the DU. No? Why is it like that? No? Because if you will implement Open RAN, especially for 5G, you will see 5G has different use cases. There's an EMBB, enhanced mobile broadband. There is what we call the MMTC, and we have the URLLC. And then those use cases requires different type of architecture to support the requirement. And for us to support that requirement, our architecture or our network must be flexible as well. That's why the separation of the hardware was proposed by 3GPP. And once we have separated the hardware, we can also flexibly define which protocol it can handle. Imagine, if you put one complete protocol into a one hardware, the hardware circuitry and components will become more complicated. It will become more expensive. But if you separate these components, define it inside this kind of DU, and one component here, and then you can produce more DU because it's more cheaper to produce. So you can easily employ or deploy an Open RAN system using or supporting a specific kind of use case like EMBB or MMTC. One of the main reasons why we are also employing Open RAN is the complexity of the network and the presence as well as the big data. So when we say big data, these are enormous amount of data that is we're getting from our telecommunication system. And the more complex the network can be, it's more difficult to handle. That's why the application of the artificial intelligence comes in, uh, especially in the deployment of 5G. Okay, so that's why implementing 5G using Open RAN will have a more effective way of deploying a wireless network. Okay, so now in this segment, we'll discuss what is 5G. This is a brief discussion only because we have discussed 5G in detail in last week. So let's get back to the different use cases of 5G. So we have the enhanced mobile broadband, the ultra reliable and low latency communications, and the massive machine type communications, or the MMTC. So you can see that different applications and use cases are now available uh, because of the 5G. And 5G has a lot of targets. We can have the 8 minimum targets for 5G, like the peak data rate of 20 gigabit per second. So 20 gigabit per second corresponds to 20,000 Mbps. So that's the capability of 5G. Now, if you're thinking about the throughput target of 6G, it could be a 1 terabit per second. So that is 1,000 gigabit per second. Okay, so that's how the evolution of the throughput requirement from each technology, from 4G, 5G, up to 6G. Okay. Now, if you see other use cases target, like the latency, it could be 1 millisecond. And in terms of network capacity, it's 1 million devices per square kilometer. Now, you will see here, the one I mentioned last time, is that the 5G has a different use cases, and it requires a flexible architecture to support it, right? For example, the enhanced mobile broadband. So imagine your system is like this. So you have the core network, okay? You have the core network, and then you have the part of the radio access network, the RAN, okay? And then you have the UE, okay? The UE. So this is your UE. Okay. So the RAN could have for example, for EMBB, for the enhanced mobile broadband. So you have the core network here. So you have the functionalities of the core, and then you have the edge cloud. So that's why we have the edge computing, and then you have the RAN. So what is happening is that you are putting an edge cloud so that the um what do you call this? The fetching of the data could be much faster. Okay, so you have that edge cloud near your radio access network. So this is the one flexible architecture that we can employ using a 5G. Now, if we will go to ultra reliable and low latency. Now, the functionality of the core, you can only have the servers here. Okay, but most of the components of the core network is near the radio access network. Okay. So probably in the core network, you can only have the billing. Okay. So very few are located in the cloud network. But on the edge part, all of the functionalities are here so that it can be a faster response of the network. Whatever the requirement of the UE, if it's less than 1 millisecond, we need to fetch faster. So that's why we are putting all the components in the edge cloud, which is near to the subscriber. That's how we can implement the what we so called the ultra reliable and low latency. Now, for massive machine type communications where it's not time sensitive devices, no. So we can put all the components in the core and then let it be the same as the typical component. So typical deployment lang. Okay, so this is how our system uh, would be deployed. Now, do we always need a physical setup like this? Not necessarily. So you can have a typical setup like this, But in terms of software and virtualization, this is where you define the protocols. Okay, so remember the protocols, the RRC, the PDCP, the RLC, the MAC. No? So you can define where are those protocols located depending on the type of use case that you want to employ in your system. Okay, so those are uh, the concepts, no, of how it becomes more flexible architecture. Okay, so as I mentioned, 5G has a lot of complexities involved. So we have a new spectrum, we have beamforming, okay, so that needs a very special algorithm to work with. So this is where your antennas are deciding where to focus the beam of your system. So it needs a very intelligent system to do this. Previously, what we are doing, um, we are physically changing the panning of the antenna or down tilting the antenna. But in this case, if we will use artificial intelligence in the 5G and then using Open RAN, the system can identify where are the subscribers are located. And then it can focus the beam on that specific subscriber or group of subscribers by itself. Okay, so using that artificial intelligence. And of course, the beamforming technology. Okay. So we have the dual connectivity, the network slicing, and this one is the cloud optimized architecture, as I mentioned previously. Okay. So this is how we implement these are the concepts of 5G. Now, also in 5G, you will see the concept of the separation of the control and the user plane. Okay. So this is where we separate these two entities. Okay. So this separation enables the network to handle different types of traffic more efficiently and then providing a better overall user experience. So the control plane, okay, the control plane carries the signaling traffic or manages the overall network architecture and delivers the essential network functions, such as, for example, the session management, the mobility or the movement of your subscribers, and the authentication. So, for example, we want to access a specific chunk or a specific slice of the network, so you will be authenticated if you have the rights to access that kind of connection. In addition, it is also used to establish and maintain communication between the user equipment or the mobile phone and the network to handle the signaling messages that are used to control the transmission of data. Okay, so that's what the signaling traffic or the control plane. On the other hand, the user plane is the one responsible for handling the actual data transfer between the UE and the network. Okay, so this is used to transmit the data packets between the UE and the network, including the voice, video, and other types of data. So to make it simpler, let's use again the analogy of the courier service like the Lazada or the Shopee. So you already completed the protocols, the RRC, the physical, the MAC, the RLC, the PDCP, okay, the SDAP, and the RRC. So you already completed, no, the packaging protocols. Now you want to transfer already. Now you will, before you transfer it, you need to go to a certain um, path. Okay. So you have the control plane and the user plane. So you put all the packages in your truck, and the truck is already ready to transmit, no, the packages to their destinations. Now the highways are the frequency, as we mentioned in the radio access network. Okay, the highways or the roads are the frequencies or the spectrum. Now before you allow the truck to use that road, it should have a certain control mechanism. Okay, so there's a gate. There's a gate. There's a toll gate. Okay. There's a toll gate. And in that toll gate, you have an RFID. Are you an RFID or an ETC subscriber? Okay, so if not, you are not allowed to enter. Okay. Or there is a security guard as well, no, in that gate. That where are you going? Okay, where are you delivering these goods? So somebody is checking and controlling where the traffic will go or where are the packages are going. So we call it the control plane. Okay, so once they have a go signal, okay, so go signal, okay, you're clear to go, you can enter the network. Now they will open the network, open the gate, and then the user plane, okay, the user plane will allow the flow of traffic. Okay, so the flow of traffic is what we so called the user plane. Okay, so this is where the carries the network of the user traffic. Okay, so that is the analogy of the control plane and the user plane. So this is a separate entity. Somebody is controlling the flow of traffic, and that is the control plane. And the flow itself is the user plane. Okay. Okay, so the separation of the control and the user plane in the 5G network architecture is one of the critical feature that enables the network to provide a more enhanced functionality and performance. Okay, so that's why it's this control, you can always see this dotted line or dash line and a and a solid line for the user and the control. Okay, so if you will see the protocol stack of 5G, it looks like this. Okay, so there is a user plane protocol stack using this different stack from the UE to the G node B. So these where the communications happening in the SDAP, in the PDCP, the RLC, the MAC, and the physical layer, and as well as the control plane protocol stack. Okay, so the protocol stack. So this is the collection of the protocols. So these are the set of rules or functions that work together to enable the communications between the user equipment and the network. Okay. So these are the means of communication happening in the from the UE to the G node B to the core network. Okay. Now, if you go to this protocol stack, you will see that there are 8 split functions. So remember the different these are the original architecture from the core network to the baseband unit to the RU. So this is the radio access network. Now, in the 3GPP approach, so this is a standard that is proposed by 3GPP. So we call it the technical reference or the TR 38.801. So in this technical reference, there is a proposal from 3GPP that we separate the functionality of the BBU into a centralized unit and the distributed unit. So moving from this architecture to this architecture will also introduce a new interface called the mid hole. Okay, so initially we have the front hole, the BBU going to RU. So this is the CPRI, and the back hole is the microwave, fiber optic, or satellite. Okay, so still the back hole. But since we are separating the BBU into two, so we need a connection. Okay, we need an interface that we will call the mid hole. Okay, so these are the new architecture introduced by 3GPP for Open RAN for 5G deployment. So this is for 5G deployment, no? So now we will use this architecture or deployment type using the Open RAN. So how do we use it, no? So if we already know the separation of the RRU, the DU and the CU, we call it the split functions, no, or functional splits. We will now define where do we put these protocols. Which of the following hardware will house the following protocols? And then defining these protocols on a specific hardware will define what type of split are we using in our network. For example, if you have the CU, if you define the RRC only protocol in the CU or the centralized unit, we call it the option 1 split. If you put the PDCP and the RRC in CU, we call it the option 2 split. So it goes like this, no? So if you put the split in the RLC, we call it the option 3, option 4 split. Okay, so if we separate it, for example, the DU house for example, the split is like this. So you have this one, the RU, the DU, and the CU. Okay. So we call it the option 2 split. Okay. Or the option 7-2 split. Okay. So it could have different names, but defining the boundaries of each split will have its corresponding name. So in this case, this is what we so call the split 2, because we have split this one, the CU into 2, into PDCP and the RRC. So you can see that the complexity of the DU becomes high because more functionalities or protocols are defined inside this hardware compared to the CU. Okay. And then there are cases that you are defining, for example, in a massive MIMO component, you are defining like this, the option 6. And then most of them are combining these two. So this is another type of split. Okay, this is what we call the option 6 split. Okay, so this is how the split is happening. Now for Open Run, most of the developers or industry experts are recommending the 7.2 split. This kind of split. This one. Okay, where the low physical layer and the RF is defined in the RU, and in the DU is the high physical, or sometimes like this. Or you can see something like this. As long as the RF and the low physical are defined inside the RU, so we call it the 7.2 split. Okay. Now, if you want to look more what is happening inside each physical hardware and the corresponding logical units is like this. So if we go for example, in the RU, the remote unit, so this is where the real-time physical functions is happening. The inverse fast Fourier transform is happening. The MIMO, the beamforming, and the RFN. Okay. For the distributed unit, so this is where the following functionalities are happening, including the error correction, multiplexing, segmentation, interference coordination, scrambling, and scheduling. And for the CU, so these are the different protocols happening as well. Okay, so this is where the logical and run disaggregation is happening. Okay, and you can see that the CU is also split into two. It's split in the user plane and the control plane. The user plane functions holds the SDAP and the PDCP. Now the control functions holds the RRC and the PDCP. Okay, so this is where the system becomes more complicated and the architecture becomes more complicated. Okay, so how we separate and assign each protocol in each hardware. Okay, and the good thing with Open Run is that using the power of SDN, is the separation of the control and the user plane. That is the software-defined networking. Now we will go to the virtualization. You will think that why do we need virtualization in Open Run, in Asia Open Run Academy? This is where virtualization will come. You will define the functionalities virtually, okay, in a virtual via virtualized network functions in a common server or a COT server. Okay. I forget the COTs, no. The COT server, no, that you can buy readily from Dell, and then you can just configure what are the different functionalities and protocols needed. Okay. So these where the virtual network functions will come. Okay. Okay. So let's take a sample of a traffic split coming from parallel wireless using the Open RAN system. You can see here, this is an application of 7.2 split, where the RF and the physical layer is defined in the RRU. And the functionality of the higher physical MAC, RLC, and PDCP and RRC and data is combined in a single BBU. We call it the virtualized BBU. So this is a combination of DU and CU. That's why I'm saying to you that if you look at the equipment physically, you cannot decipher if it's a open run or a typical run component, because typically they're the same. But the difference comes in the functionality inside what's happening in those equipment. Okay, and this is the typical core network. Okay, so this is a typical split 7. Now, what will happen if it's split 8? Okay, if it's split 8, you will see physically it's the same RRU and same BBU, but the functionality inside is different. Now, in the split 8, you will see the component of the RRU is defined with an RF protocol only or RF functionality only. And the other functionalities like physical, MAC, RLC, PDCP, RRC, and data is defined in one hardware only. So we call it the traffic split. Physically, in terms of hardware, you will not see any difference. But in terms of definition of the protocols and functionalities, there's a big difference. Okay, so that's the difference between split 8 and split 7. Okay, split 8 and split 7. So physically, well, there's no significant difference, right? Okay. So if you will summarize, why do we need a split? No, why do we need to do a split functionalities? So as I mentioned, there is a need to support specific use cases per technology in per use case in the 5G technology, like the EMBB, URLLC, and massive machine type communications. And then there's also support for specific density and load and demand per given geographical area. And of course, the available transport networks with different performance levels. And then you will see the different summary of each functionality. So this is where this is your CUDU. It's a combined it's a hardware where you combine the CU and the DU functionality. So this is where the split 2, the RRU. So this is the one where the RRU becomes more complicated. So meaning the RLC, the MAC, physical, and the RF are defined inside the RRU. So it will correspond to higher cost because the circuitry inside this RRU will become more complicated, right? And then if you want to deploy more RRU on site, and then you only want to deploy a basic LTE or basic GSM or 3G call, what the experts are proposing is that you only define the RF component in the RRU, and the other functionalities in the CUDU split so that you can produce less expensive RRU because the circuitry is very simple. Okay, so that's the one of the main drivers why we are doing these split functions. It depends on the type of application and of course to efficiently save on cost. Okay, so we don't need to define all the functionalities in a single equipment only. Because imagine you have an equipment like this, no? So you put everything in the RRU, and then at the end of the day, there are no subscribers. Oops, sorry. There are no subscribers there and nobody's using it. It will be considered a sunk cost, meaning you are just wasting the the functionality or the potential of your equipment. It's just like buying a Ferrari and then you're not using it. Nobody's using it. Okay. So this is the summary of the run split or the logical view of the run split. Okay, so the mobile operators need the flexibility to pick and choose different splits based on the same COTS-based hardware, okay, and network components by using different software implementations. Okay, so this is where the Open Run will come in. Okay, so as I mentioned, Open Run is um, we are opening the interfaces, we are opening the hardware, and we are opening the software. But opening these components does not necessarily mean we are opening everything for the sake of security issues, no? So it's not like that. So when we say open, everything that is happening inside the equipment is transparent to every players that is involved. But before we arrive in Open RAN, the radio access network also evolved aside from 2G, 3G, 4G, and 5G. So it started with the traditional network. So we call it the distributed RAN. So the distributed RAN is where the baseband unit and the radio unit are located on the cell site premises. Okay. Now it became centralized RAN. Okay. So the C RAN. So the centralized RAN is where we put all the baseband units into a central office and then we pull it. We call it the baseband hotel. So we use the dark fibers to connect all of these radio units and to the baseband pool. So what is left in the cell site are the radio units only. And then the next step after centralizing the baseband unit is to virtualizing the functionalities. So we are using commercial off-the-shelf servers, yeah, the COTS, okay? And then we put it in the cloud, okay? All the functionalities has been virtualized, okay? But the main problem here is that even though the functionalities are virtualized, it's still proprietary. We still don't know what's happening inside. Although we have an overview of the protocols, standard protocols, but the main reason why there are some equipments not talking to each other is still invisible to us. So that's why virtualized network is still not an open RAN system. Okay. Now, the true openness comes in the Open RAN. Okay, so we have implemented the split functionalities. Okay, and then you can also virtualize the functions, but you can use commercial off-the-shelf servers, and the interfaces are also open. So meaning you can mix and match all of those equipment, including the software. So this is where the true openness comes in, the Open RAN. Okay. Although the traditional vendors are proposing this, but still on the proprietary side, still on the black box setup. Okay. So when we say open, it means open source software, open source hardware, and open interfaces. So the main goal of this opening the RAN is to have an interoperability standard for RAN elements. Okay, and then open means is an intentional capability of the software and hardware and interfaces, but is complying with an agreed upon standard like 3GPP and of course open uh, ORAN alliance. Okay, now this is where we are discussing the open RAN ecosystem. Okay, so what are the different groups, no? So first in line is telecom infra project, tip. Tip was founded in 2016 by Facebook, or what we so called now as Meta. So they are an engineer, this is an engineering focus and collaborative group that is assigned for designing and implementing global telecom network infrastructure. Okay, so this is the first um, industry group that initiated Open RAN. Okay, so TIP Telecom Infra Project. So if you want to learn more of TIP, so you can just visit their web page at telecominfraproject.com. Okay. So next is Oran Alliance. Oran Alliance is formed in 2018. So they are promoting open and intelligent RAN. And this is the second organization driving the Open RAN movement. Okay, so it's a combination of China Mobile and then other Chinese vendors like CRAN and CRAN Alliance and the XRAN, no? Which is coming from the American side, the entity Docomo and Japanese vendors, no? So they combine each other, so they merge and then form the ORAN Alliance. So if you compare the difference of TIP and ORAN Alliance, what are the differences between them? Well, Oran Alliance creates and promotes and enforces the standard like a 3GPP. So if you want to look at the standard, what are the different standards? You go to Oran Alliance. They are the one creating the standards. Okay. Now, if you want to more on the deployment and execution, okay, and open run ecosystem, yeah, or guarantees or certifies the suppliers. So this is the task of Telecom Info Project or TIP. So there is no overlapping of responsibilities between the Oran Alliance and the TIP. When it comes to environment setting up an environment for Open RAN system, it goes with the Telecom Info Project. But if it comes to specifications and standard, it goes with the Oran Alliance. So that is the difference of TIP and Oran Alliance. Now, in terms of software, there is another organization. We call it the Oran Software Community or Oran SC in structure. So this is funded by Linux Foundation. That's why if you will experience on the configuration of Open RAN, it's based on the Linux. Okay, because it's based on this ORAN software community. Okay. The other Open RAN group includes, like, for example, Open Networking Foundation or ONF. Okay. So this is an operator-driven community led non-profit consortium fostering democratizing innovation in software-defined programmable network. So they are starting to program their network. No? Okay, so we call it the Open Networking Foundation. Now, if we look at the small cell or the in-building solutions, there is another group for that. So they call themselves Small Cell Forum or the SCF. So they develop their own Open RAN environment with the small cells or the in-building solutions. So these are the radio access network that you can see inside the buildings. So they call themselves a small cell forum. And then we also have this Open RAN policy coalition. So this is a collection of firms created to support policies that would accelerate the adoption of open and interoperable solutions in the RAN as a method of creating innovation and stimulating competition. So it was launched in 2020, so it's still very young, no? Okay. So the Open RAN Policy Coalition goals is that they fund research and development. They remove the barriers to 5G deployment. They also avoid the heavy-handed or prescriptive solutions. And then they also use the government procurement to support vendor diversity and also signal government support for open and interoperable solution and support global the development of open RAN and interoperable wireless technologies. Okay, so that is the function of the Open RAN Policy Coalition. So there's a lot of entities supporting Open RAN, no? Including also if you will see the market of Open RAN. So there is already in a semiconductor market, so in chipsets and components, the services, the software, the cloud, and the hardware. And then you will see familiar logos already or familiar companies that start to involve in the Open RAN ecosystem. Could be a software, the hardware, or even the chipsets, or even the cloud. And then if you look at the global landscape or landscape of Open RAN, the two prominent entities deploying Open RAN now massively in the entire world is the one in Japan, which is Rakuten Mobile in Japan. And the other operators like NTT Docomo and KDDI are starting to study and partner as well with other operators. And on the other part of the world is the Dish in the US. So Dish is a new company operator. So it's a greenfield operator that deployed Open RAN completely in their network. So if you can see, deploying an Open RAN is easier for a greenfield operator. When we say greenfield operator, they are building their network from the ground. So it's the first time that they will build a system. Comparing with a matured network like what we have here in the Philippines, it's very risky for them to change out their equipment from traditional to Open RAN. Just imagine you have a house, no, and then suddenly they say, Open RAN is more intelligent, no. So before you upgrade from one house to another house, you need to think twice or thrice or more than that, because number one, it will involve cost. Number two, it will involve trainings. Okay. Number three, a lot of headaches in terms of implementation. And number four, a lot of business risk. Okay. So there's a lot of thinking that's happening before somebody change from Open RAN to from traditional network to Open RAN. But for new greenfield networks, like Rakuten and Dish, it's a easy decision for them, no, to go for an Open RAN because they don't have any traditional network in their system. Okay, so it takes a lot of study before they want to deploy it. But for matured network, one of the deployment scenario that we can use is the rural sites. So if there are areas that still not covered by traditional network, we can still build additional cell sites or radio access network using Open RAN. That's what we are proposing to our GDAS areas, though those geographically isolated and disadvantaged areas. If it's still costly to build a cell site there, why don't you choose Open RAN instead? Okay, so it's much cheaper, to implement, and you can also have a good use case or study to deploy it in your network. Okay, yeah. So those are the different trials and the global landscape of Open RAN, and that ends our discussion. So some key learning points before we end this session. So RAN means radio access network, And RAN is the part of a cellular network that gives mobile coverage. And Open RAN means Open Radio Access Network. And yeah, Open RAN is an industry movement to develop a disaggregated and interoperable radio access network using a general purpose processors, software-defined technologies, and open interfaces. And we have a lot of RAN groups and initiatives that supports Open RAN. And Open RAN trials and deployments have been done in different parts of the world, especially in Japan and in US. Okay.